Welcome to Atal FDV on recent trends in renewable energy. I taken an opportunity to welcome the expert of session 9, Mr. Sandeep T. Patel, Assistant Professor in Mechanical Engineering Department, Government Engineering College, Valsad. Mr. S T Patel has completed Bachelor of Engineering in Mechanical Engineering from SVM Institute of Technology, Bharuch, Gujarat in the year of 2004. Master of Technology in CAD/CAM from the Sardar Vallabhbhai National Institute of Technology, Surat, Gujarat in the year of 2009. He has completed his PG Diploma in Intellectual Property Rights from IGNOU in the year of 2016. Mr. S T Patel has a total academic experience of 12 years and industrial experience of 4 years. His area of specialization and the research is vertical axis wind turbine, gear transmission, and rapid prototyping. Mr. S T Patel has published 4 research papers and filed 2 patents. It is an honor and privilege for us. Mr. S T Patel is with us. Today, Mr. S T Patel is going to deliver expert lecture on recent trends in the aerodynamic analysis of vertical axis wind turbine. So his deliberation and the expertise on the topic will benefit the participants. So I invite Mr. S T Patel for the expert session. So Mr. S T Patel, you can start your session.
Thank you very much, sir, for a very humble introduction. Am I audible to everyone?
Yes.
Yes, sir.
Yeah. Thank you, sir. So, as sir mentioned, I don't consider myself as an expert in this domain because the knowledge is like a sea, and I could able to whatever absorb I can. So, this is the last session, and I understand that all participants are exhausted. The aerodynamic basically is the subject which is not our core domain for mechanical or electrical. I have seen the participant from various domains. So this is something different. So I'll try to keep it in a way so that everyone can understand the things, and I try to minimize the mathematics expressions. Okay, let me start the PPT first. As we are talking, wind energy is an indirect form of solar energy, and it mainly caused by uneven heating of atmosphere, rotation of earth, basically due to coriolis effect, and the unevenness of earth surface. Fine. It may be a global wind pattern or it may be a local wind. So there are some globally reasons and there are few local reasons. The flow pattern of wind is affected by earth terrain like hills and valleys. Bodies of water means sea or river or lake like that, and the forestation, as well as it may be natural, it may be man-made, like buildings and all that man-made stuff, and natural forest, right? So this all irregularity of surface causes the variation in wind. Now, wind energy means what? It describes the process by which we generate mechanical power or electricity using kinetic energy of wind. Fine. Now I don't say the drawback, but the limitation of wind energy is like it's a low level energy compared to other energy sources, including solar. It's a low level energy having a low potential, and it is not continuously available. It is always varying. It depends on so many factors. Like during midday, the wind would be highest. During midnight, it would be again take a peak. But in meantime, the variation is there. Now, let's have a glance of a little bit of history of wind turbine. Now, this technology is very old. It is claimed that the first wind turbine was incepted 3,000 years back. There are no physical evidence which we have, but still, there are remains of windmills on a border of Afghanistan, the area called Sistan, and it is from 7th century. So it is almost thousands years old. Fine. More than that. So here the term is used windmill. And I'm talking about wind turbine. So when we say turbine, turbine means what? It converts kinetic energy into useful mechanical energy. So there are so many other devices you can say that we do the same thing. So what is different about turbine? So turbine is basically a rotary component. It has a rotary motion. So these are the two traits of a turbine. But when we say windmill, it is application. So it is one kind of turbine, but it is application specific. So in older times, the wind turbines were used to grind grains. Fine. So that's why they called windmills. Aate ki chakki. Fine. And other application was to pump the water. Fine. So these are the two main application in older times where the wind turbines were employed, and that's why this term windmill has been coined. Now, when we are using the wind turbine to generate electricity, the mechanical power which wind turbine generate, we convert it using the generator into electricity. Then it shouldn't be called windmill. That's a wrong term for that. Oh, okay, so layman's generally use the windmill and wind turbine as a synonym, but that we shouldn't do that. Fine. So first electric generating wind turbine was first erected by '40 years. So it's almost 1.5 century. So that old wind turbine technology is existing, right? So it's not new. Always linked with the commercialization. If there is no commercial potential, then that research may slow down or it may not.
क्वेश्चन नंबर पण घ्या
की पण दिसणार आणि क्वेश्चन नंबर पण दिसणार की
ID
आपण देतोय आयडी
म्हणजे
क्वेश्चन नंबर तो तिथे इन्सर्ट करायलाच लागतो आपल्याला आणि तो क्वेश्चन नंबर
How to yeah, we must have to move to the renewable sources of energy and reduce the consumption of
Your voice is breaking.
Okay, so there are political wills, there are public will that helps. So as a researcher, our job is to make this technology efficient. So is 2,355 gigawatt, which is the almost 1/3 of the total energy we produce on the globe. It means all the sources, renewable as well as non-renewable, out of that 33% of electricity we produce is out of renewable sources. That is a good thing, but that is not enough. That must be increased marginally, right? But it is happening slowly, steadily, but it is happening. Now, this includes all other energy sources. Let's break it off. So this data was 2 years old in 2018. This is the recent one. So this is a graph of last 2 decades, starting from 2000 to 2020. You can see the major resource of renewable energy throughout the globe is hydro energy, right? But the increase in hydro energy is very, very, very low. But it gives a fair share. Okay. And why it is so? Because it's a continuous source of energy. Continuously, we can produce electricity. But from the data of last decade, last 10 years, if you observe, there are 2 sources of energy, which includes solar and wind, are increased very, very rapidly. These are the 2 main contenders which are increasing globally. Fine. So if we focus basically on wind energy, this is the last 20 years progress. So here you can see the very rapid growth you can see in last 5 years or 10 years in wind energy production. Fine. It's a global data. This is country-wise data. So where we stand, as in India, where we stand. So only for wind energy, globally we rank 4th. Fine. China is producing maximum wind energy. US is 2nd, 3rd is Germany, and India is 4th. Yeah, but here the consumption of energy in India and China is very large compared to what we produce. Okay, there are some European countries, including Germany. They are producing marginally high compared to their total consumption. Denmark is extraordinarily placing the wind turbines wherever it is possible. So almost 50% of their consumption is out of only wind energy. Okay. And the majority of wind turbine technology research is happening in Denmark. There are 2 great universities. One is called DTU, Denmark Technical University, and TU Delft. These 2 are working towards wind energy rigorously. If you go for a research publication, their majority research came from the Denmark and Germany. Fine. Now, as a growing market, especially for wind, our growth of last year in fiscal year of 19, it is 4%, which is 3rd in whole world, while China is extraordinarily booming, 44% growth in wind energy market, particularly onshore. Offshore, we are not interested. India is not putting any offshore wind turbines till now, due to maybe some political or geographical reasons. But there is some good news I found in one of the articles. There are 2 main drivers why India is doing better in wind energy sector as well as solar also. That is, first reason is very high demand. If we are very highly growing market, So our energy demand is high, and again, political ambitions are associated with it. So by 2022, 175 gigawatt.
Contribution करेंगे बस.
Yeah. Someone's. Yeah. Thank you. So by 2022, 175 gigawatt total energy is targeted by government, and out of which 60 gigawatt is only came from wind. The target for 2030, total target of 2030 from all renewable sources is 450 gigawatts, which is very high, and in which almost you can say 25% is came from wind-based generation, which is 140 gigawatt. So the future of wind energy is bright in India. That directly implies research in wind energy is bright. So there may be there must be some opening soon in research funding by the government through the collaboration or any other mode. So if you are interested in this domain, it's a good time to get in. Now, let's come back to our core topic, which is wind turbine aerodynamics. So first we need to understand about the wind, its behavior, and
other acts of sexual harassment can be.
Yeah, please keep your microphone mute. If you have any question, you can unmute and ask instantaneously, not an issue. Okay, so wind energy, wind behavior we need to understand first. So what are the requirement of wind particularly for wind turbine? So this table just give you a rough idea about the wind classes, which is good, excellent, outstanding, or just fair. So generally, if we go for commercial wind turbines, design range of a wind speed is starting from 7 to 12 meter per second. Depends on the size and shape of wind turbine, but it is generally lies between that. If we go for smaller wind turbines, it ranges from 4 meter to 10 meter per second, right? Or more than that. But for a larger commercial turbines, it is ranging from 7 to 10. Now, wind is varying with location to location. It depends on the geographical location and geographical conditions. So we must know the behavior of wind in particular location if we want to place a wind turbine over there. For that, wind measurement is essential. So there are many ways to do that. So most reliable way is to practically measure the wind at that particular location. Okay, so that measurement includes not only the velocity, but the direction, temperature, pressure, humidity, etc. Right? And the span for that measurement is generally up to 1 year or more than that. So this image shows one wind mast. Wind mast is nothing but a tower. On that tower, at different height, various wind measuring devices are installed, and measurement is recorded continuously. Right? Hello. Yeah. So am I audible?
Yeah.
Fine. So at different height, the various wind measurement devices are installed, which includes anemometer, wind vanes, thermometers, barometers, etc. So if we plot a graph of a wind velocity with the time, it would be very complex one. So what we need is average speed throughout the year or a month, or generally it is throughout the year. Year wise average data, what we need. So for that, some statistical analysis has to be carried out. So variable probability function is proved to be very, very closely matched statistical function with the wind behavior. And it is accepted throughout whole research community. So other probability functions are Rayleigh function, which is also a very good one, but Weibull gives you a more realistic probability function. Fine. So based on that, we decide the average wind speed, and that average wind speed will help us to design or calculate aerodynamic behavior of a wind turbine in order to design a wind turbine. Fine. So Weibull function is mentioned over here, and for various shape factor, the graph is shown over here. Fine. Another way, if you don't have money or a time to measure wind speed, then we can use wind maps. So this is approximate data, not exactly pinpointing data. It's at a larger scale you can get that data. There are so many agencies. This image I have taken from the Global Wind Atlas project, sourced by DTU. Another one is CWAT, which is Indian organization, and you can buy data from them at very cheap cost for particular latitude and longitude. Fine. So here you can see at different height. So there are two maps. At first is at 50-meter height and wind speed at 50-meter height, and second map shows wind speed at 100-meter height. So one observation you can carry out is that the whole coastal area has fairly good wind speed. There are few locations in Karnataka and Rajasthan, including Kutch. The wind speed are high. So you can find out so many wind farms over there where horizontal axis wind turbine has been installed. Right? So for a research purpose, you can go with the wind map data to estimate the wind behavior or wind measurement at particular location. So now come back to the difference what we are discussing. Though majorly there are two kind of wind turbine. There are a lot many other, but commercially we can see two wind turbines. One is called vertical axis and another is called horizontal axis. So the difference is their axis of rotation. In horizontal axis, the rotation axis is horizontal, so it must require some sort of column to support, means it has a structure to provide the hub some elevation, while vertical axis wind turbine directly can be mounted on a ground itself, okay, because its axis is vertical and it can take wind from any direction. Majority of commercial wind turbines are horizontal axis due to its superior efficiency, okay, due to superior efficiency. So why if horizontal axis is superior, then why we need vertical axis? So there are few reasons where horizontal axis can't work. we can use vertical axis. So those scopes we can find out, and vertical axis wind turbines can be useful over there. Fine. So as horizontal axis technology is more mature because more research has been done, as its efficiency is superior and got commercial success throughout the years. Now, basically, this whole wind turbine development occur during 70s, 1970s. So if we see the history, wind turbines were used many years back, like thousands years. We are using it. First electricity generating wind turbine we have installed 140 years back. And what we are talking right now is just 50 years back, commercialization of wind turbine has started. So why that long? Because we have, till that, we have unlimited source of renewable sources. Non-renewable sources like coal and petroleums. But in what happens in 70s, if we look into history, OPEC union was generated. This all Saudi countries has made one union called OPEC, and they have controlled the oil supply, and they have put a ban on few big countries like Russia, America, and some European countries. So due to that, oil shortage and rationing was occurred in those countries. Even India was affected. So they have to move to the another source of energy, and that gives boost to the renewable sources like solar and wind. Fine. So in 1970s, this whole research and development has started for the wind energy sector. But in few decades, they found out that horizontal axis is more superior, having a longer life and commercially viable. So more research was focused on horizontal axis turbine. And that's why it is nowadays, if we see, it's more mature. It is having a great potential compared to vertical axis. But still, there are so many things which is remaining to find out about the vertical axis wind turbine. Okay. Now, in 1990s, the Sandia laboratory, I'll come back to that again. Sandia laboratory in USA has started researching with the vertical axis wind turbine. They have done the majority of research in vertical axis wind turbine, but due to the construction made out of aluminum and lot of fatigue stress is happening, and the turbines were failing. So they lost interest and they put the project down, and people just leave the vertical axis wind turbine now and then. So as we discussed, the almost HWT has, I'm going to use abbreviation. Horizontal axis wind turbine is as a HWT, and vertical axis wind turbine as a VAWT. These are the standard abbreviations for wind turbines. Now, the good thing is there are so many designs which of a VAWT survived at small scale. So for small wind turbine sector, VAWT is a very good candidate compared to horizontal axis wind turbine. There is a possible niche market for VAWT in location like high mountains or an area where very gusty and strong wind is happening. Okay, the wind is for horizontal axis wind turbine. What we need is a constant wind supply. The variation should not be very high. It should be constant. That is the good wind condition for horizontal axis wind turbine. But VAWT, on another hand, they can sustain gusty wind, large impacts. So same goes with the urban areas. So nowadays in Gujarat, we see that government is promoting solar rooftop systems. As we don't have any energy storing capability, they provided with the option grid connectivity. So that makes a good offer to every household to invest in their rooftop solar power plant. Fine. It may happen after 10 years, smaller wind turbine you can plant at your rooftop and that get connected with the grid. So that is very, very much possible. So that is one of the research potential in VAWT. There are many other reasons, including they have low level of noise and they can accept wind from any direction. It means no pitching joint. The turbine starts at the speed is called cut-in speed. And there is some design limit at which we need to shut off the turbine. That is called cutout. Strong wind. So that limit of wind is called cutout speed. So HWT generally having cutout speed 25 meter per second maximum, while for VAWT in theory it can sustain up to 65 meter per second wind speed. So that makes it superior in case of very gusty or very high wind regions like in high mountains. Fine. Another point is it can sustain, or basically it is insensitive to extreme weather condition as heavy snow, freezing rain, frost, salt, sand, humidity, etc. Okay, a simple example I can give. At your home or office, if there is a ceiling fan, you can observe after a few days the dust particle will sediment on the leading edge of a fan blade. Fine, that happens. Why that happens? That only occur on a leading edge. Why? Because the wind at the leading edge velocity will be 0. So whatever contamination or dust air is carrying, it is going to sediment over there. Fine. Throughout the time, if that sediment become larger, it affects the aerodynamic performance of that particular rotor. Our ceiling fan are not that much sensitive to a small sediment, but wind turbines are. Same goes with the snow. In India, snow is not a general phenomena, but in other country it is. Same goes for rain and all that. So vertical axis wind turbine, majority of are insensitive. They don't get affected with these things. Fine. So that makes them robust and maintenance free. Otherwise, horizontal axis wind turbine has to be cleaned in periodic times. Fine. Okay, not the history, but the inception of VAWT. So there are two fundamental vertical axis wind turbine on which the whole VAWT technology has built it. So basically, there are two types. One is 7S turbine, second one is Darius turbine. 7S turbine was patented on 1929, while Darius turbine was patented on in 1931. The inventor of 7S turbine, the name is 7S Sigurd Jones. So from his name, the turbine name was coined as 7S turbine. Similar goes with the Darius turbine. The inventor name is Darius George Jean Marie. Fine. Now, if you see the dates, this is again give you a very good historical perspective. The majority of engineering and aerodynamics happened during the bad times, worst time in humankind. And in last century, the worst time was First World War and Second World War. But the positive side of that is the great engineering invention occurred during that time. That is due to the need of that particular time. So all the aviation occurs in that era. Why? Because people need fighter planes. Okay, who has the better fighter planes, that wins. So in Second World War, many countries has used fighter planes, and for that they have made a lot of research in fundamental aerodynamics. Right. This two rotor inception date lies between First World War and Second World War. Fine. So what we are going to talking today is almost 100 years old technology. Fine. But still, the research was started in 1970, so only 50 years back. Okay, so 7S turbine is basically drag type. Why we call it drag type? Because the main driving force for this turbine is drag force. The principle of moving the turbine for 7S is drag force. While for Darius turbine, it's a lift force. So that's why we can segregate as a lift type. So we can categorize VAWT in three major segments: drag type, lift type, and third one is hybrid. You can just make use of drag type and lift type, combine them, and you can have a hybrid turbine. There are many other types, but fundamentally we have this two categories only: drag and lift. Fine. So our further discussion will be more focused on lift type turbines, various lift type turbines, including Darius, because you can correlate the drag type similar to lift type turbine as far as aerodynamic is concerned. Right. Drag type has some limited scope compared to lift type, so I have decided to go with the lift type. Fine. Now, these are the various type of VAWT. You can see the first what Darius has invented. The shape is called Troposkin shape. Troposkin shape is made by just rotating a rope on an axis. If you held to end of a rope and you just rotate it, due to its momentum, it takes some shape. So when you do the rope jumping, the whatever shape rope makes is called Troposkin shape. Right. That is due to the shape is chosen because of balancing of stress. That is another area. Now, there are few simple and complicated version of this one. The most popular is a fixed pitch H rotor. We call it straight bladed Darius turbine. Straight bladed Darius turbine. So more focus will be on straight bladed Darius turbine because nowadays the research is moved toward it. So this is one timeline graph. You can see during 90s, as I told you earlier, the conventional Darius research and their commercialization was rapid in USA basically. You can see the rate things in North America. North America means Canada and USA, and blue as in Europe, and green as in Asia. So in Asia, only China is doing that for vertical axis wind turbine. So after 90s, it gets slowed down. Why? Because when you commercially plant a wind turbine, to know whether it is performing well and it achieved the life expectancy which engineers have proposed, it takes 10 to 20 years fine to realize that. So that's why it takes that much long. And afterwards, after 90s, it almost for 10 years nothing happened due to the bad publicity of VAWT, and after 2010 it againly taken up, and mainly by the Denmark and Germany. Fine. So right now in 2020 Germany has installed a 1 megawatt horizontal axis wind turbine, but unfortunately that was a false prototype, and unfortunately within a 6 month one blade break off, and they have again installed it in 2022. So we need to see whether how it is going to perform. It may open a new era for vertical axis wind turbine in a mega scale. So this timeline only shows the turbine which are more than 100 kilowatt capacity. 100 or 100 more than 100 kilowatt capacity. Smaller turbines have another market, and in which VAWT is a ruler till now. So before we get into the aerodynamic techniques of rotor, we need to understand basic aerodynamic terms. First is called lift. It's a force vector which we apply on a center of pressure of an object perpendicular to the incoming flow. Now, what is center of pressure? So center of pressure is we can compare it with the center of gravity. In case of aerodynamic, it's called center of pressure. So at center of pressure, all the aerodynamic force moment are zero. Fine. So with the change in wind speed, with the change in orientation of a body, center of pressure get changed. It is unlike center of gravity. This center of pressure get changed. So there is another term called aerodynamic center, but that is a talk for another day. So lift force can be computed by this equation, which is FL, lift force is FL, is equal to 1/2 rho V square ACL. Now rho is density of air, V is the ambient velocity over here, and A is the frontal area of an object, while CL is coefficient of lift. So coefficient of lift is a non-dimensional entity or a number which we frequently use to define aerodynamic behavior, lift behavior of an object. So more streamlined object has more lift, while bluff body does not have that great lift, but they have a great drag. So every body, it may be a streamline, it may be a bluff. There is some amount of drag and there is some amount of lift. But compared in streamlined body, in particular orientation, compared to lift, drag is very, very low, negligible. While in bluff body, compared to lift, drag is very, very high. So that's why we don't bother sometime to show both lift and drag for a particular case. Okay, so drag is opposite to lift. It's a force generated due to the incoming flow in direction of incoming flow. Okay. Now these are the terms which we use to quantify the aerodynamic behavior of particular body. First is called coefficient of power, CP. So it is like an efficiency of a system, but in this case, aerodynamic system. So CP is ratio of the maximum power obtained from the wing divided by total power available in the wind. For example, wind turbine extract 40 kilowatt, while in for that wind, the total energy is 100 kilowatt. So 40 by 100, it gives you 0.4 CP. It means 40% efficiency, you can say, aerodynamic efficiency. Fine. So the equation would be T omega. T is torque, omega is angular speed, 1/2 rho A U cube. U is ambient velocity over here. Similarly, coefficient of torque, it is ratio, nothing but the ratio of torque developed by the rotor divided by torque available in the wind. Third important quantity is TSR. We call it tip speed ratio. In order to compare the behavior, we compare CP against the TSR, tip speed ratio. So what is tip speed ratio? It is a tangential velocity of a tip of a blade. Blade means a rotor, tip of the rotor, divided by the apparent wind speed. Okay. And finally, the solidity. It is the ratio of overall area of blade over the swept area of the turbine. Now, this equation written over here is in only applicable for straight bladed Darius turbine. So direct derivation is written over here. So solidity of straight bladed Darius turbine is NC by 2R, where N is number of blades, C is the chord of the blade, and R is the radius of the rotor. Now, before starting or before jump into rotor aerodynamics, we briefly discuss the Bird's theory. Now, Bird's theory is the fundamental theory of aerodynamic for the wind turbine, which defines the ideal, define the efficiency of ideal rotor, or in other term we can say it defines the limit of energy you can extract from the wind. Beyond that, you can't. Fine. So there are few assumptions for the Bird's limit. This is very much common things in mechanical engineering. Also, you must have learned this one. But here, 2-3 things I want to mention. Here, the friction drag is considered to be 0. Total number of blade is considered as infinite. So it is like a solid disc, but the blades are infinite. So it is assumed like that solid disc may, the wind can get across that solid disc. Fine. The thrust over the rotor area is uniform. Okay, and there is no wake at all. In actuality, there is a wake after the wind turbine. But here, in this theory, we are assuming there is no wake. So, once stream tube is assumed, now you must understand few fluid dynamics terms like strake line, streamline, path line. So you understand, then and then you can understand the stream line and stream tube concept. So stream tube is just tangent line to vector velocity field. Fine. So it at a particular instant of time, it represent the direction and of flow, okay, where it is going. But it may happen with time it get changed, but it is only valid for a particular instant of time. So here the assumption is there is a stream tube boundary in which our disk infinite number of actuator disk having infinite number of blade is kept, which is cylindrical. So U1, U2, U3, U4 are the different velocity at different places. At the entry, it is U1, and at the exit, it is U4. Just before the wind turbine, it is U2, and just after wind turbine, it is U3. Before wind turbine, the portion is called upwind portion, and after wind turbine, the portion is called downwind, the downwind portion. Fine. So let's apply a conservation of linear momentum theory. According to that, basically the thrust is moment into change of velocity. Fine. So U1 minus U4 into mass flow rate into change in velocity. So mass flow rate multiplied by change in velocity. So that mass flow rate can be represented in rho AU form. So this is one equation we are getting through the linear moment conservation of linear momentum. Another theory we can apply is Bernoulli function for these two control volumes in upstream and in downstream. Fine. 1, 2, and 3, 4. These are the two control volumes before rotor and after rotor. So for before rotor, the Bernoulli function will be equate like this. Now Bernoulli function do have three heads: one pressure head, kinematic head, kinematic energy head, and third one is potential energy head. Now here the elevation is same at every point. So naturally the potential energy is going to be zero. So only two head, pressure head and velocity head, kinetic energy head we are comparing for the both volumes. Now if we go for equation of thrust, it is nothing but a pressure difference multiplied by the projected area of a rotor. So P2 minus P3 multiplied by A2 will give you the thrust force acting on a actuator disc. If we put value of P2 and P3 from these two Bernoulli functions, we get equation like this one: thrust is equal to 1/2 rho A2 and multiplied by U1 square minus U4 square. Now from both equation from the equation of conservation of momentum and Bernoulli, we get relation U2 is equal to U1 plus U4 by 2. Let's assume one axial induction factor A is equal to U1 minus U2 upon U1. By substituting this two equation, we are getting U4 is equal to U1 1 minus 2 alpha. Now let's find out the power of that rotor. So that is nothing but thrust multiplied by velocity. So using the derivation from Bernoulli function, we can find out the P value. Now in this equation, if we substitute value of A, we get this equation: P is equal to P in terms of rho A, U and A. Okay, so now equation of coefficient of power CP, rotor power upon power in wind. Power in wind, as we know, 1/2 rho A U cube, and the rotor power we have derived. So the expression for CP for an ideal rotor, what we are getting is 4A multiplied by 1 minus A raised to 2. Now we want to find out maximum CP. So for that, we can derive this equation of CP with respect to A and equate it to 0. In that case, A will become 1/3, and that gives you a C value of, if we substitute that value in equation of CP, we are getting CP max, which is approximately 0.59. It means 60%, approximately 60%. So that is called Bird's limit. So for an ideal rotor, the maximum energy you can extract from wind is 60%, precisely 59%. You can't extract more than that. It is not theoretical possible. If you prove someday this, you can using some rotor, you can extract more energy, you get the Nobel Prize. Fine. So this is just a rough comparison of various rotor for the CP versus TSR. Now the green line depict the Bird's limit, while all other rotor are depicted over here. So you can see the 7S has very poor efficiency, which is less than 20%, while maximum Darius can achieve is 40%, while propeller type horizontal axis wind turbine can achieve up to 50% of efficiency. This is somewhat comparison. Okay, so next step is to find out the power in the wind. Okay, so total power available from the wind is power we want to obtain the maximum power what the rotor can obtain. So maximum power available is 1/2 rho AU cube. What we can obtain from the wind using our rotor is power is equal to 1/2 rho AU cube multiplied by Cp of that particular rotor. If you are taking the example of straight bladed Darius turbine, the frontal area would be H height multiplied by the diameter. So here, as per this figure, it would be 2HR. So that frontal area is rectangle. In case of horizontal axis wind turbine, the frontal area would be circular one. Okay, so as we are talking about lift type turbine, we need to understand about airfoils and their behavior. So this is airfoil terminology, basic nomenclature over here. So main thing is there are two kind of airfoils, symmetrical and unsymmetrical. Symmetrical turbine airfoils, let me show you. Yeah, symmetrical airfoils have symmetrical shape from that chord. Okay, while unsymmetrical airfoil, this is chord, so upper profile and lower profiles are different. If we draw a mean line joining leading edge and trailing edge, this green line is called mean camber line. If we are joining leading edge and trailing edge with a straight line, that is called chord line, and the length of that is called chord. So chord is one of the important function. There is another term called camber. Camber is the maximum difference between chord and the camber line. So here the maximum camber is depicted. Fine. Now, how the lift happens. So there is one great saying by Philip Sparlett. Now, who is Philip Sparlett? He is a physicist, particularly his work in turbulent modeling of air is very popular. If you have used some CFD software, there are some models, turbulent model, Sparlett-Adams model. So that is basically made by him. Apart from that, he has developed 2-3 other models. Fine. So he has given a great contribution in the domain. What he has quoted that it is easy to explain how rocket works, but explaining how a wind works take a rocket scientist. So I'm not a rocket scientist, so I'm unable to explain you how actually the lift occur and wind works. Yeah, I have idea, but it is a whole lot of time consuming thing to explain. So I can say there are, I have included over here, because there are people think this is easy, and due to this social media universities, there are a lot of controversy and misunderstanding happens over the lot of videos like YouTube. If you go to YouTube, a lot of video you can find out which has a wrong misconception given about lift concept, and same goes with our textbooks. In schooling, in order to simplify the things, there is one explanation in which it is given that the particle which is fluid particle which is moving in upper edge of a airfoil move faster in order to reach at the tail, while at a lower end the particle is moving slower, so that both particle start at same time and reach at same time, start at same time from nose and reach at same time at tail. That is a complete wrong thing. Fine. There are two popular explanation given by two great scientists. One is by Bernoulli and second one is by Newton. So both are inadequate to explain it completely, but when we combine them, you can get the idea about it. So you can refer a good book by I forgot the name, but the name of the book is Understanding the Basic Aerodynamics. You can search it. Yeah, so this is what happens when air strike on a airfoil. So here we are talking about symmetrical airfoil having horizontal orientation, let's say. So the pressure and velocity at ambient air before the wind, before the airfoil is P0, V0, far away from the airfoil. Similarly, after the airfoil far away, the pressure and velocity is V0. So when we hit at the leading edge, you can see the graph, the velocity is becomes 0 at leading edge. Same happens at the trailing edge. So static pressure is inverse to that. Velocity is 0, then pressure is highest, maximum. Fine. And then after airfoil, it gets stabilized. Okay. So if we plot the lift occur due to upper surface and lower surface get balanced over here because the geometry is symmetrical. Okay, so there is zero lift if your blade is horizontal. But if we tilt it by some amount, what happens? Tilt it vertically by some amount, what happens? The lift, negative lift occurring on a lower profile is lesser than the positive lift. Okay, I am just making this explaining this thing in a simplified manner. It is not like that. You don't take word by word explanation in that manner. But the resultant lift is positive in upward direction, and that is why wing of an airplane or wind turbine experience the lift force in upward side. Okay, so this is the resultant thing. There is a wind, relative wind. Why we are called relative wind, I'll explain you later on. Due to that, there is some lift force and there is some drag force, and resultant force is total aerodynamic force. We can represent it on a center of pressure. We can calculate it on a center of pressure. So you have seen this 2D representation of lift throughout the surface. So this is a two-dimension theory, essence of two-dimension theory, where we are assuming that length of our airfoil is infinite, but in actuality it is not infinite. Our airfoil has finite length. So in actuality it looks something like this. Fine. So having a finite length wing, at different section, the chord wise pressure distribution or lift force is different. At a mid span it is highest. So the resultant average representation is made on pressure center line, or aerodynamic center line is made on this lower image, B image. Again, yeah. So this red line represent the lift distribution. Now, why 0 at the edge? Because at the edge the pressure should be ambient. So this is the we can say this is a relative pressure as well as lift diagram, both would be same. Now, so as relative pressure at the end is 0, the lift force is going to be 0. Okay, so it has some parabolic shape. If we want to consider a uniform lift, then we can take an average. Okay, then our lift force, average lift force would be like this straight line. So that is a simplification of our actual practice. Fine. Okay, so with angle of attack. Now, what is the angle of attack? So this is the relative angle between the chord line and direction of relative wind. So with change in angle of attack, what happens? This is depicted over here. If the low angle of attack, the lift would be low, because you can see in a first two videos, topmost videos, first video show the animation for smoke lines. The same concept with the bubbles, charged particle bubbles is shown, which shows the better vertices. So here it is, flow is very streamlined. You see, here the flow is very streamlined. So lift is very small. If we increase little bit angle of attack, medium angle of attack, the lift will increase. But if we excessively increase, what happens? The detachment of flow occurs, and due to detachment, the drag force will increase marginally, and due to that, loss of lift occur. Fine. So same thing we can apply with the aeroplanes. Fine. So this is the behavior. Now, if we plot the graphs, so there are two airfoils are depicted over here, symmetrical as well as unsymmetrical. If angle of attack for unsymmetrical blade is 0, then also it will have a lift force, because the geometry is not symmetrical one. So in both case, for different Reynolds number, means for different wind speed, if we plot lift diagram with lift coefficient against angle of attack, so you can see the graph increase linearly. With an increase in angle of attack, lift coefficient increase. It means lift force increases. But after some time, the stall condition occur, and due to that, loss of lift occur. So for example, if we take Reynolds number, this solid line Reynolds 3 into 10⁶, then after 15 or approximately 15-degree angle of attack, the loss of lift occur. Fine. So this particular airfoil, whatever shape it may be, I'm not giving you that particular value. The operational range of angle of attack would be 0 to 15 and design angle of attack would be 15, because at that degree we are getting the maximum lift. Is it so? No, it is not, because the drag coefficient also increase with the angle of attack. Fine. So what would be the maximum lift condition? So we have to take ratio of CL and CD, lift coefficient divided by drag coefficient. At whichever angle of attack that ratio is highest, that is our design angle of attack, and this is how we can choose design angle of attack for a particular airfoil. Now, this airfoil performance we can measure or predict. Fine. So there are two methods, as in all the design methodology, either computational method or experimental method. So computational methods has some analytical methods which use panel codes. There are two great codes already available: Xfoil, which is developed by MIT, and Rfoil, developed by DTU. So on DTU website, Rfoil is available. Same way, Xfoil code is open source. Rfoil source code is not available, but Xfoil source code is open source. You can access it. You can install it. There are some tools also available which directly use that Xfoil code. So this is one of the great website in which you can find out majority of airfoil data as well as the performance, because they have incorporated Xfoil code into it. So in a single click you can have whole performance parameters. So now this example I have taken, NACA 008. NACA is a profile developed by one niche agency of USA during benchmark profiles and many. So the full form is National Advisory Committee for Aeronautics. You can search it and you can get the equation of all airfoils and their details. Or you can use this website, airfoiltools.com. Here, let's say I want to measure NACA 18 at 10⁶ Reynolds number. So I can simply have a Xfoil prediction in form of graphs as well as Excel sheet. You can also download the Excel sheet for the same from this source data file. Fine. So here the result you can see, maximum CL by CD for this particular airfoil is 77.0 at alpha 10 degree, means our design angle of attack is 10 degree. And how you can get this CL by versus CD graph, you can see this highest point is at 10 degree. Okay, so this graph, CL versus CD, CL versus alpha, CL by CD versus alpha, CD by CD versus alpha, and CM versus alpha, all these 5 graphs are called airfoil polars. Fine, they are better known as airfoil polars. So if you have a polar airfoil polar data, you have whole aerodynamic performance of a particular airfoil. So these are the computational tools freely available. Another thing is you can go for CFD analysis. We'll discuss it in detail for the whole rotor part, but another way of doing it is CFD tools, but it is bit time consuming compared to Xfoil, and it requires some sort of experience and expertise to perform a good CFD analysis, which is having results nearer to the real data. Fine. And finally, we can always go for experimental methods. Wind tunnel analysis is that you can go for that. So wind tunnel is a device which produce wind at certain velocity which you aim for, and the flow you can control. This is the some wind tunnel we made at our college. It's a homemade, you can say homemade wind tunnel. Now in wind tunnel you can control the wind speed, you can control the turbulence of the flow. So wind parameter you can control, and in test section you can put the object you want to analyze, and you can measure the aerodynamic performance of it. So how to measure aerodynamic performance of a airfoil? So there are 2-3 ways. One of the recent and advanced ways to put pressure transducers inside airfoils. Okay. Before that, people used to put tubes and which is connected with the manometer. So it requires a lot of space. So for a smaller airfoil, it was not possible. For nowadays, there are digital pressure transducer available, and they are very small in size. So you can incorporate inside the airfoil. Okay. Secondly, there is one technology called PIV, particle image velocimetry. This is very advanced and sophisticated technology, but again, it's very costly this affair because it requires CCD camera charged coupled display camera, and it is a bit costly. What principle it uses is that in flow they put some tracer particle which flow with the air. Laser light is applied on the flow, and a high speed CCD camera captures the image. Okay, so between two images the data analysis is done using a very high computing computers, which does the trace and track operation. So let's say 2 frames of image are there. So in first image the particle is over here, so that is traced. Okay, second image of in second image, the job of that image recognizing software is to find out where that particle went. Fine. So using some spatial algorithm, they trace that, okay, this is the particle which was previously over here. So track and trace using some sophisticated algorithm they do, and by that the whole flow field reconstruction can be done. So velocity can be measured, pressure gradient can be measured, as well as vorticity and turbulence. These all things can be measured using PIV, which is not possible with the traditional manometer techniques. Fine. Okay, these are the few preferred airfoils for VAWT, which includes NACA symmetrical and unsymmetrical. Few of them are developed by DTU and few are developed by other researchers. So let's move to the working principle of Darius VAWT. So this is a process geometrical parameter of Darius turbine. This is a force equilibrium diagram of VAWT. Now you can see, let me start the pointer. Yeah. Here. So U infinity is our up wind speed, ambient wind speed, while W is relative wind speed. Okay, so what is the difference? Now, we are assuming that this rotor is rotating by some tip speed ratio. Okay, so velocity of this rotor, tangential velocity of rotor is V, while U is the ambient velocity. So there are two relative moments which our rotor is going to feel. Okay, like assume that you are sitting on a rotor. Okay, you are sitting on a rotor and rotor is moving. Let's say air is stationary and rotor is moving. Or make it more simple, you are in a train is moving, air is steady. So what wind you are going to feel? At whatever speed train is moving, you are going to feel the same amount of wind. Fine. Let's assume another scenario where air is flowing towards you as well as train is moving in opposite direction. So what happens? The relative wind, what you are going to feel is speed of train plus the speed of wind. So that total relative speed of wind you are going to feel. Same thing over here. Instead of linear motion, it's a rotary motion. So we are considering tangential velocity component and U velocity. So ultimately, the W vector is a relative wind which airfoil is going to experience, and the total is U vector plus V vector. Fine. Now, so if we plot force equilibrium on a single airfoil, so W is our relative wind, and due to that, in that direction, we have a drag force FD, and perpendicular to that is lift force Fn. Fine. So if we resolve in tangential, these two forces in tangential and normal direction, so Ft and Fn. So on rotor, you can see Ft is the force which is responsible to rotate the rotor. Okay. Now, here the theta is called azimuth angle. So with the change in azimuth angle, this Ft is going to change. Okay. We'll see that later on. So the equation for Ft and Fn would be like this. It's a simple trigonometry, and this is for particular angle of attack, and that angle of attack depends on the azimuth angle basically. So for a whole revolution, integral of Ft will give you total tangential force, average tangential force over one revolution. Okay. And once we calculate the tangential force, the torque would be Ft into R into N. N is number of blade, and power would be torque multiplied by angular velocity. So these are the affecting performance parameter on straight bladed darius, which includes solidity, number of blade, pitch angle, aspect ratio, which is height to radius ratio, okay, blade aspect ratio, etc. Fine. So if we measure or calculate CP for different tip speed ratio, the graph would be something like this. So at the highest value of CP, whichever tip speed ratio we are getting is our design tip speed ratio, and that rotor must design for design tip speed ratio so that it can achieve maximum efficiency, and that depends on a weight of a rotor, okay, and its dynamics. So that is another part after the aerodynamics. Now again, as we discussed for airfoil, how to calculate the performance. So there are again three methods: mathematical methods, analytical method, CFD method, and practical experimentation methods. So first we'll start with the analytical models. So there are few analytical models which are popular for vertical axis wind turbine. One of them is momentum model. There are total 3 momentum models, but their main drawback is that they are not valid for large high tip speed ratio and high rotor solidities. Right. So if the tip speed ratio is low and solidity is low, then this may perform good. So there are one by one we'll see. First is called single stream tube model. So in this model, the entire turbine is assumed to be enclosed within a single stream tube as shown over here. And this incorporates the actuated disk theory into analytical prediction model of our Darius wind turbine. In this stream tube, induced velocity is assumed to be constant throughout the disk, fine, and it is obtained by equating the stream-wise drag with the change in axial momentum. So conservation of axial momentum is applied over here, fine, and stream-wise drag is calculated, okay. As we seen in 1D momentum theory, we have put on a horizontal axis wind turbine sort of disk. Here, instead of that, we are considering rotor as a surface of imaginary body of revolution. Okay, so in Bird's theory, what we have assumed, it is modified for vertical axis wind turbine, fine. I'll not get into the calculation detail of this. I'm just giving you how this works, fine. But this model is so simple so that this result are not reliable. So there is another variation of it which called multiple stream tube model. Because in single stream tube, we are considering there is only one blade, fine. While in multiple stream tube, what we do, we divide the stream tube into multiple stream tubes, and the total swap volume of turbine input divide into series of adjacent independent parallel stream tube, fine. Just say as shown in this image, fine. The blade momentum, elemental momentum theorem is applied in every stream tube individually. Okay. But here only lift force calculation is done for the induced velocity. Another variation of multiple stream tube is made by Parachute. His name is too complicated for me. The only book available for vertical axis wind turbine is written by him. Fine. So you can go for design of vertical axis wind turbine with emphasis on Darius rotor. The name of book is like that, and that is the only book available in market for especially for vertical axis wind turbine. So what he has introduced is double multiple stream tube model. So he has divided two separate region for upstream and downstream, and both region are again divided with multiple stream tubes. Okay, so this model basically gives a good correlation between experimental results compared to single stream tube and multiple stream tube model. So this is a somewhat better model. Okay, then comes vortex model. This is the considered to be most accurate compared to every other model. But their computation is very expensive. It is very time consuming, and sometimes the conversion problems is always there. So what it does, it basically potential flow model. It create a potential flow model based on calculation of velocity field around the turbine through the influence of vorticity in the wake of blades. So in image you can see the vortex sheet having different bound vortexes. So by calculating the strength of this line vortices, the lift coefficient of airfoil can be determined for a particular set of inputs. Then comes a cascade model. This model is well suited for high solidity turbine. Right? It is also for low, but if the solidity of turbine is high, this is the model which we can rely on. So what is cascade? Basically, the periodic arrangement of several blades. In turbo machinery, we call it as a cascade. So in this model, the aerodynamic characteristic of each element of a blade are obtained independently, similar to our double multiple stream tube theory, and they are assumed to be positioned in a planar surface. By keeping the interspace between two adjacent blades as their circumference distance, as you can see over here. Okay. So this model is also bit expensive on calculation part. So to conclusion, we can derive that vortex model is based out of this all models, so you can go for that, but rigorous coding is required for that. There is no freely available code is available for that. Another technique is computational fluid dynamics, CFD. People are generally obsessed with CFD because it shows a very beautiful plots, beautiful results. But the validity part is required always in this case. There are a lot of good softwares available, including ANSYS Fluent, ANSYS CFX, Cosmol, Star CCM Plus, OpenForm, etc. Fine. My preferred software is Ansys Fluent. It will give you a better result in case of vertical axis wind turbine. You can go for Star CCM Plus or OpenForm as well. Those are also good softwares. OpenForm is open software. You can use it freely. Fine. So there are three stages: pre-processing, solver, and post-processing. So in pre-processing stage, what we do, we define geometry, we define the physics of wind, we define the elemental shape, size, etc. We call it meshing. And in solver stage, we applied with the physical models. And finally, in post-processing, we obtain the results in form which we want. Fine. So first we talk about the geometry. I'll only discuss the salient feature of this one, which are not readily available. So it may be a two-dimensional analysis. It may be a three-dimensional analysis. I always go for two-dimensional analysis because there is no computing power available with me which do three-dimensional jobs. This two-dimensional analysis also take almost 2-3 days to solve, and believe me, it is with the high power engines I'm using, i7 and almost 18 GB RAM and all that. Fine. So it is bit computationally heavy on machines if you are doing a proper analysis. So there are two kind of, recently the people are not doing the steady state analysis. The transient analysis is preferred, which varying with the time. In this one, we are defining the domain, moving domain. So rotor domain is moving, rotating. Fine. So there are two mesh we generally define: a stationary domain and rotating domain. Rotating domain is basically a circular shape in which the airfoils are cutted. To further optimize, we can keep the rotating domain in a ring shape. In that case, you have to define two interfaces inside. So this is the interface with the stationary and a rotating domain, and this is outer interface. While here only one interface is there. Fine. So that this make is more simplified version. So if you have a central shaft, you have to go with this. Obviously, you have to go with the circular domain. But if you don't have a central shaft, you can go with the ring domain as well. So out of these two, you can choose whatever you feel. Generally, the size of domain is crucial. If you keep it very small, due to the wall boundary layer effect, the results will not give you a proper idea. So it should be a large enough. But with the increase in domain size, the computation time increase exponentially. So that is again a true. Fine. So generally it is upstream is 10 hour, downstream is minimum 20 hour. Nowadays people are keeping it 100D. Fine, 100D, not 20 hour, 100D. And over here 40D, upstream is 20D. So that much large domains are preferred nowadays. Same thing in a three-dimensional, you can define cylindrical or as well as the ring domain like this. Now, it is important that you create a very fine mesh. So finer the mesh, more the element, more the computation time. So there is always a catch where to stop. But at least nearer to the surface of an airfoil, your mesh should be structured and fine enough so that it can create a boundary layer effect. Fine, it can capture boundary layer effect. Otherwise, this would not end up in a good simulation. Then other crucial part is turbulent models, which physics model you need to choose. So there are a lot of turbulent model which are preferred. I have listed down the 7 most popular turbulent model for the same. Among them, K omega models are giving you a better result with reasonable amount of time. So if we couple it with the detached eddy simulation model, the profile would be very, the captured behavior of air would be very, very similar to the actual one. But it sometimes, many times it has a problem of converging. Okay, so that it is hard to converge, but it give you a beautiful result, give you accurate results. So K omega SST alone is a good solver to use. Fine. And finally, the result you will find in, let's say, torque coefficient by degree is in a revolution if we see. So if you track only one blade, the torque profile is varying with the azimuth angle. Fine. So it is getting peak and then negative torque occurs, but average torque would be positive. So here with the solid line, the total torque, you can see it has 3 peaks and 3 valleys because 3 rotors are there. So this is a theoretically and experimentally valid behavior. Oh, am I audible still?
Yes, sir.
Yes, sir.
Okay, okay, okay. I'm asking because I'm running through mobile, and whenever some call occurs, the network may get tempered. Fine. So this is what you get. Now, another thing is wind tunnel analysis. I have put together a video from MIT lab, and they have made this wind tunnel analysis for straight bladed Darius turbine in a full scale model. It's a large wind tunnel, large scale wind tunnel, and they are operating on a full scale wind turbine. So this is to give you an idea how large is this tunnel is, right? So this kind of analysis is a bit expensive, very, very expensive, right? In India, we do have such kind of tunnels. It is in IIT Kanpur. You have to book before few months to get an appointment over there. Other are private tunnels or defense tunnels. So our best chance is in IIT Kanpur, fine. For a big scale tunnel, small scale tunnels are available in many institutes. The last thing what we do experimentally is called field testing. So generally, when you are commercializing the turbine, this is important. It is essential, and it is give you a reliable aerodynamic as well as structural performance, right? And it is always done after theoretical or wind tunnel analysis, right? So what they do, they put the turbine in an area having a good wind speed condition over a large period of time, fine, for a 6 month to 1 year. Okay, and they give you a results of performance data throughout that time span. Fine. So this is one video from Stanford University, what they have done for straight bladed turbine. It's a actual field testing. Yeah, so it is 5:46, and I have just in a nick of time I have finished. Thank you for listening so patiently, and thank you for that trouble made by internet and without complaint you joined. If you have any question, we can answer them. In between, nobody ask any question, but if you have any question right now, we can. I'll try to answer them in my
Hello, sir.
capacity. Yeah.
Hello, sir.
Yes.
Good evening, sir. Your presentation is very nice, sir.
Thank you.
And one thing I want to ask, your experimental setup and all these videos, it is find that this research work is not possible without funding, sir. So how you can choose that this topic as your research work, sir?
Yeah. If you go through my profile, I haven't published a single paper in this domain due to lack of the same thing, because I am lagging with the experimental data. Fine. So I'm more relying on CFD, but I have done one patent in the same thing. So yeah, you are right. It is difficult to conduct such research with limited resources. So we tried to put together a wind tunnel with our own money at our college, and we have built it, but it is lagging with the measuring equipment. Fine.
Yeah, yes, sir. Same thing I am facing. So that's why I'm
So,
asking.
okay. So what you can do, you can go for a field test. Fine. That will give you a trend. So that is equivalent. Okay, but that field test require a time. So you need to fabricate your setup before almost 3 to 4 months in order to get data of 4 months of a field test. Are you getting me?
Okay, sir. But sir, why you are choose this is your area of research, sir?
Yeah, this is one of my research area. I am recently working with the rabbit prototyping, but I'm basically interested in small wind turbines. How to
Okay,
improve that performance so that we can use it in our urban applications.
okay,
Right?
okay, yes.
And no query from the participants, then I take the opportunity to thank Mr. Sandeep Patel for sparing his valuable time and discussing that vertical and which is uh, basically need for the current scenario for the urban areas. So I thank Mr. Sandeep Patel for sparing his valuable time and
Yeah,
discussing
thank you
that
very much,
huge.
sir, for considering me and your whole team for putting an effort to organize such event. Thank you very much, sir.
Thank you.